Hello everybody, welcome back to the video. I'm not even sure how long it's been. Honestly, it's been so long. Um, like, I don't even know how long it's been because every time I try to record a video, my hardware just says no. But hopefully, this works. So, my throat is weird. I want to show off this thing I made. I call it Star Calculator. Basically, the way that it works is this. I actually have this little dot here. And this is the theoretical position of the planet, and then this is the model of the planet, and this model exists to kind of show you what the planet would look like, and where is it? Oh, it's up here. If I click this button, the planet will start orbiting. Currently, the time rate is about 1 day per second, but obviously, that can be changed. I can move the planet around, and you can see the ice caps melt as we get closer. And if we get too close, then the equator will start to melt, and then, run away. It's not perfect, but it works pretty well. If we get the planet really close, it'll start to orbit really quickly, but also, it'll, turn orange, and yes, technically this planet is larger than the star, just so you can see it. But this is a star calculator and a planet calculator, so, mostly it's based off of the star. So, if I open up star presets, we get this. There's a lot of stars in here. Not really sure how to organize it, so it's just kind of like this. So say we want an M3V. Well, we can load up that type of star. You can also see it has a temperature. It's a temperature-based color, not a proper color-based color. I could probably fix that at some point, but I don't know. I really don't know what I do. On this side, we could take, say, an A9V. Very larger star. This one's actually larger than the planet. And it'd take a while to even get a habitable planet. I'm not really gonna worry about that at the moment. O-type? Yeah, sure, an O9V. Very bright star. The planet, even out here, is going insane. If I use an O3V, yeah, this was the farthest I was able to find any data on. I was using Wikipedia for this, so there's not really an O2, O1, or O0V, because, well, can't find anything on it. Here I've got stellar remnants, so, like, if I turn that out, this kind of works like this. This planet, yeah, this planet is kind of really large in comparison, but here is a white dwarf. If I can go to the largest white dwarf, which is, well, significantly larger. Not that much larger, but it's a lot brighter. As we can see, it's a lot brighter. Wait, how does it compare to the sun? Probably doesn't compare to the sun at all. Whoa, brighter than the sun. That's weird. No idea why that is. Oh, because it's more massive than the sun. Radius is still tiny. Well, actually, radius should be smaller. Yup, smaller, I think? No. Hold on, what? Okay, I'm confused. Well, I used actually, no, I used a proper data set for this, so I had no idea what on earth happened there. Not sure why a white dwarf is brighter than the sun, but, might have to fix that. Then we have quasi-stars. I just added these. These are the best values for this. I'm sure they're more realistic values. But there weren't any values for me to work off of, really. So I just came up with some. So even the smallest quasi-star is massive. If I place a planet precariously on the inside of that bound, it's still on the inside of the larger quasi-star. Dang it. Yeah, I'm sick. That's got a problem. So if I bring the sun in, oh my goodness, y'all might be hearing, my sibling out there. Um, yeah. So, unsurprisingly, if I bring in the sun, it's a lot smaller. A couple real stars. Here's Betelgeuse. Oh, I like how the inner bound of the habitable zone is smaller than not that habitable zone. The inner bound of the red zone is smaller than the star. Here's a much smaller. Here's most massive star, and the VY Canis Majoris because it's massive. Right. Yeah, VY Canis Majoris is massive. Yeah, I was making sure my eyes weren't being stupid. Of course, sadly, VY Canis Majoris does not compare to Quasi Star. Actually, the smallest one, I guess it does. Huh, I don't know. That's the star presets. I'm gonna go back to the sun, cause the sun is really easy to use. I'm gonna put the planet back in here. Um, not quite where the Earth is, but whatever. It does have an actual orbital calculation. I mean, that's not really that impressive, but you know, if I put the planet where the Earth is, it should take about 365 seconds to go around. Where is T? Bop. T is gonna be set back to 0. Um, time rate in days per second. Oh, I see, because every 20 milliseconds it goes by a 50th. So this is in days. So now if I crank this up to 365, it should orbit about once a second. It's a bit laggy though, so it won't necessarily do that, but about once a second. And then I'm just gonna stop time. Well, I can stop time like that. Yeah. So now this is already nice. However, what if you want, because you know this habitable zone is for water. This is pretty well defined. However, where is it? Where is it? Where is it? No. Goldilocks zone calculation. Solvent presets. So this is for like if you have different completely different biologies if you want to like make sci-fi stuff, since this is meant for world building. So obviously if I grab water, it's just normal. However, for methane-based life, the planet stuff exists way out here. And so I need to go out here. And as you can see, the planet looks way different. Now I'm not sure why the planet in the habitable zone is mostly frozen. That seems to be a problem. I suppose it's because it needs more of an atmosphere, right? Because if I go over, where is it? No, not in colors. Oh yeah, albedo. If I raise the albedo, obviously it'll freeze. If I lower the albedo, it'll be a lot warmer. And the atmospheric optical depth. Oh, I like it. It's only like that at 1. If I crank it up to like an actual atmosphere, like 10, the albedo's gonna have to be way higher for life to exist here. In order for it to be kind of Earth-like, but with methane, we need these stats. I have no idea if that's realistic or not. I don't know enough, frankly. Uh, Whatever. I'll keep albedo relatively normal. Um, yeah, by the way, there's a water cap, no, well, methane cap in this case, but still. What about 2? Will 2 look good? 2 will look alright. Now, however, I can use other liquids too. Ammonia? Well, for ammonia, it's frozen, so our planet is icy. If I bring it into a very precarious habitable zone, oh, it's also messed up. But we can see a very blue liquid. A lot of these are blue, which led to problems because I really, what is it? It's 4-3. Yeah, this looks like a weirder version of Earth. Um, what else have we got? We've got more. The further you go down, the weirder the solvents are for weirder situations. And I know a lot of these aren't realistic, obviously. They don't have to be, right? Realistically, water is the only known one. Methane is you know. It's plausible. Ammonia, maybe. The rest, no. But it's fun to have them if you want them. I mean, brimstone is probably my favorite because, well, it goes so far in, right? Like, it lets you imagine planets that are, like, really close to the star and still habitable. There's also one more thing. I don't remember one more variable. Oh yeah, these variables exist. So space. What is it? This is S. Okay, so E. I think. Yeah, E is the scale for empty space. So in this case, it's 1 to 100,000, or one unit. One. Wrong button. One. One Desmos unit is one is 100,000 kilometers. And then this is a thing for specifically the star, for scaling the star. So if I drag it around, if I make the scale stronger, the star is smaller. By default, though, these values are the same because, well, just makes sense. Where is it? There is a specific and important Goldilocks zone. It's in here. Evo strength. I don't know why I call it Evo strength, but basically what it does is it's like how much optimism do you put in the prospect that life could survive, right? So if I'm very confident. I think life has a very good chance of thriving. Well, the habitable zone engulfs, it actually engulfs the frost line there. And if I say no, I don't have much faith, it's actually a lot smaller. I mean, in this case, it's still there. But if I were to move to say water, it makes it very small. Um, but I would suggest putting it at 0 so that you get the actual habitable zone. So I didn't quite explain what these other lines are. So this outer line, the blue line, is the frost line for the material that you've clicked on. So obviously in this case we have the water frost line, um, which is useful for having. It's useful for where there's going to be a lot of water. For instance, if you want to do subsurface oceans, they're going to be outside of here. I don't know how I'm going to handle that, but they're just going to be out there. And then the interior line, the red line that's in here, is I don't know exactly what to call it. It's the rock line, right? Inside of here, rock would melt roughly. That's not calculated the best. I just kind of used a temperature to calculate it. I don't know if it's accurate or not, but it's what I chose. So I think it works. Um, yeah. That's about it. I can't think of any other features that this thing has. Um, I mean, there is the nice effect that you get when things are glowing. I suppose I can show off, if I go back to Brimstone, a feature that I like, which is that even when the planet is really hot, when a planet is really hot, so if I go to water, I think it's hot enough to start being reddish. Yeah, it's got a slight reddish tint, right? Well, if I go over to Brimstone, there ain't anything. Okay, hold on. Okay, why is there nothing showing up? But when I do this, there's a slight amount showing up. Oh wait, wrong thing. Here we go. The rock should be reddish, and that should be reddish too, but I'm not seeing it. Oh wait, no, you can see it. You can absolutely see it. Because the rock gets kind of more bluish as we go out. So yeah. Yeah, it exists. It's just difficult. So yeah, there you go. I think that's everything. Bye bye. Bye everyone.